A third type of sedimentary rocks are organic sedimentary rocks. Organic means from a living thing. Okay, a little different than the definition you may know of in the grocery store when you're shopping in the organic section, but that's what it means. So, I'm going to start with this. This is a swamp. Good picture of a swamp. What you have here, a lot of vegetation and a lot of standing water. Now think about this over many years. What's going to happen? Leaves will fall down into the water, and they will. They tend to not decompose when they're under the water. There's not a lot of oxygen in the water, so they don't really decay. And then they will pile up, and you will have layers and layers of leaves. And trees will fall down, and they will stay under the water. They really won't rot or decompose. And that, if that was to happen for thousands of years, tens of thousands, hundreds of thousands, millions of years, you have these big swamps in one area, you will get a pretty amazingly thick layer of leaves, trees, bushes, etc. All of that dead plant life at the bottom of the swamp. And that can often be hundreds of feet thick. Okay, that is the origin of coal. Okay, if you want to copy those down, if you have this. Okay, coal is from plant remains. So what will happen is like you have hundreds of feet thick of those plant remains. The ones on the bottom have a lot of weight. They really get compacted. Being that pressure and being down that deep will cause them to heat up, and that heat and pressure will actually transform it into coal. So the deeper it is and the more pressure and the more heat. Now, I don't think metamorphosis rocks, heat and pressure, but it actually will transform that from less like leaf wood material to become more what you know of as coal. Wood can burn, and coal is even like, it's kind of more concentrated, so it burns even better. It burns a smaller amount, gives off a lot more heat, and coal is very good for burning, and is still used around the world for burning it for heat, energy, electricity. And these diagrams show it here. This is 300 million years ago, and it shows there's a swamp, there's water accumulating dead plants. This jumps ahead 125 million years later. The time here is pretty unbelievable. It's 125 million years later, and what you have, the swamp no longer exists in that area, but you still have those plants down there. Now you have sand on top. This is would be exaggerated a lot more. It'd be much thicker. But it's in there just to show how it changes. And then it jumps 135 million years later. What you may see is not this, but you see that sand has become compacted and cemented to become sandstone. And then this, which is called peat, so that in between, it's less like plants and leaves, it becomes peat, which you may have heard of. There are peat bogs, like Ireland is known for their peat bogs, and it's this compressed dead plant material. You can burn it. It doesn't burn that great. It doesn't burn as great as coal. It's kind of smoky, and a lot of people do burn it, actually. But that gets compacted more, and the heat causes chemical reactions, and it be transformed into coal, which is what we have here. And again, very good for burning. It's an organic sedimentary rock. Coal with sandstone on top, and that guy looks pretty angry. Look out. Okay, here's a picture of a type of limestone, another type of bioclastic sedimentary rock. This is called coquina, and you probably can see this is made of pieces of shells, broken pieces of shells that have been cemented together. So think about at the beach, a place where there's a lot of beds of clams that live, or oysters, scallops. They live kind of in that shallow water near the beach, and they end up dying or getting eaten by birds or fish, and then the shells end up in the waves, and they get moved back and forth in the waves, smashed on rocks, smashed on each other. They get broken up into pieces, and what's going to happen? You have these layers underneath the water of just broken up shells, and then you have mineral precipitate out between them. They get compacted, cemented together, and you can have a rock like this. Next up is a close-up, and if you had this in your hand, you really can see like little pieces of shells. It's very obvious. It's pretty cool. A type of limestone. Limestone, usually the origin of limestone is like the shells of something that lived in the ocean. Is usually the origin. Here it's just very obvious. Okay. Oftentimes limestone, it's much smaller organisms. It's a little more complicated, but that's generally the source of it, and that picture is good to see it. Another part of sedimentary rocks that I'm going to talk about is, and I think this is cool, that sedimentary rocks, just the type of the sedimentary rock, can tell us where that section of earth, that section of the crust was when that rock formed. And I'm going to refer to the depositional environment as what it's called. So for instance, sandstone, well, where do we see sand? We see sand at the beach. So if you see sandstone, that area, wherever that sandstone is, was probably a beach, or at least near the shore, a beach 100 feet out, 700 feet out in that area where the sand is. And then that sand was buried, compacted, cemented, became sandstone. So it's sort of these clues as to the past, which is cool. Siltstone is going to be the sediment itself, the pieces will be finer than sand. So that tends to get carried out by rivers when they enter the ocean. It gets carried out further. It doesn't settle out as quickly. In water, the larger the pieces are, the faster it settles on the bottom. So you have a rock the size of your fist, it's going to go right to the bottom. It's not going to get carried out very far. Sand will get carried out and settle down, again, pretty quickly. But now as you get into silt, is really small. And clay particles, like the finest of mud, they get carried way out into the ocean. They can get carried out miles in the ocean. It could take weeks, months for it to settle to the bottom. So that's why I have shale is made of clay. So 5 to 50 miles out, in that range, maybe a little more, that is where the shale will be settling out, and you have this fine layer of mud. It takes a long time to build up. We're talking, that much a year. It's probably a pretty fast accumulation of shale out there. Once you start going 1,000 miles out from shore, there's no more of that sediment from land, from the rivers, is going to be carried out that far. It's all settled near shore, and you're not going to have any of that clastic sediment 1,000 miles out. You have different kind of sediment out there, which is also cool, from things like chalk, the rock chalk. We're not really going to talk about that right here today. So these, when you see shale, you get a sense, oh, this is kind of deep water, 300-400 feet deep on the continental shelf. Gives you a sense of where that was. Conglomerate has bigger particles, pebbles, so that was closer to shore because that stream is not going to carry those pebbles out very far. Whenever that stream slows down, the pebbles kind of stop right there. It doesn't really get carried out because they're larger. If you see layers of coal, that tells you, it's like a clue to the past, that there was a swamp there at some time when that coal formed. Rock salt, layers of rock salt. In places you see rock salt layers, that are 50, 100 feet thick, and that says in that area there was some sort of ocean or that got cut off, became an inland sea, didn't have water flowing in and out. Then it was warm enough for the water to evaporate, and then all that salt is left behind. Also, totally cool. Limestone, if you see limestone, generally limestone is from, not the kind of we saw there, but the usual type of limestone. It's usually pretty gray in color, pretty nondescript looking. You can't see much in it really. Those kind of deal with, they're formed by really smaller organisms that live in the ocean and their shells, and then sort of piling up and precipitating out of the ocean water. And that only forms in warm, shallow water close to shore. We know that. So, for instance, I live in New York State, and we have a lot of limestone in New York State. But off the coast of New York and then the Northeast, the water's too cold. Limestone would not be forming there today. We know that. So that tells us all the limestone we see here, it needs to be around warm water. Where's warm water in the world? It's near the equator is where there's really warm ocean water. So much of the limestone that covered New York, and again, there's a lot, was formed when, it's crazy to think about, think of continental drift, when all of North America was closer to the equator. That's when the limestone formed, because that's where it was near the warm water. And then, after that time, the whole northern North America continent drifted further northward, away from the equator, towards the pole, to where we are today. Crazy. Which is good, because we use limestone. Limestone is the key component. It makes up cement, which is the key component to concrete. Concrete is pretty much sand, gravel, you add water, and then you add cement to it that it keeps it all together. So basically, if you don't have limestone, you can't make concrete. It'd be hard to think of a modern world without concrete. Is one of the main things we rely on and we really take for granted. And if you another thing I like to think about in sedimentary rocks, that concrete is really just a sedimentary rock that man just kind of makes in the shape that they want, where they want. I like thinking of that. As a matter of fact, we often take rocks, break them apart like limestone into cement, and then we take rocks, break them apart into the components, move them somewhere else where we sort of transform them or make them into another rock of the shape and in the area that we want, which is totally cool. I think it's totally cool. Is that what I just had? That is what I just had. Okay, so this is a side view, a stream going into the ocean. It's faster here, it's going downhill, and once you hit the water here, the speed really just slows down. So and sometimes these rocks, even a rock about this big, or even the size of your fist, the water tends to roll it along the bottom. Water has a lot of force, but once it gets here, it's not going to roll it anymore. And some of the, and then the smaller pieces, maybe they get going faster and they'll get carried out here. Sand will be like mixed in with the water, and sand will take some time to settle out through the water, but it will, as it goes out, the sand starts settling, will end up here. It's the finer particles, silt and clay. Now that stuff is sort of in that muddy water. You guys see muddy water, and that will take a long time to settle out. Again, it can take months and months to settle out. So that will tend to drift out further. So you have silt out here, which is again a little smaller than sand, and clay, the smallest, gets carried out further. So this is a good cross-section view of the pattern of deposition that we see. Back to this picture, I love this picture showing it. You're going to have larger sediment here, and as you go further out, the sediment gets smaller and smaller. Another good picture, and this is La Plata River, and I like this because you see the sediment in the water. You really can see it, and you can see that there's more sediment here, and it probably settles out. The bottom of this channel here, or whatever this is probably very heavy with sediment, and then the finer stuff does get carried out. You see it getting carried out. Love that picture. Okay, now this is labeled actually, and I have a few things. This is called the mouth of the stream. It's where the stream empties out into a larger body of water, a lake, an ocean. I have it labeled here. The sediment size decreases, and we call that horizontal sorting. It's sorting because it is in order. Larger sizes here, a bit smaller, and then the smallest out here. Sorted as if someone sort of put it in some kind of order as opposed to being random.